Okay, so optimization. Optimization is a special tool that we use in calculus to find the most efficient way to solve a problem. These problems focus on trying to maximize or minimize a certain quantity, and this quantity is subject to the given constraints put forward in the problem. With different problems, you maximize or minimize different things. For land problems, you might want to find dimensions to maximize the plot of land, or minimize the amount of fencing required. For business problems, you may try to achieve maximum profit or minimize costs. But ultimately, with optimization problems, you're trying to find the best results. And that is what optimization is all about.
There is specific procedure for solving optimization problems. First, you have to read the question carefully. Identify the variables and organize the given information with a picture. Next, identify the object function. Write it in terms of variables of the problem. The objective function can vary. Identify the constraint. Write them in terms of the variables of the problem. The constraint is equal to a fixed value, equal to what is given. Now use the constraint to eliminate all but one independent variables of the objective function. With the objective function, expressed in terms of a single variable, find the interval of interest for that variable. Use calculus to find absolute minimum value or maximum value of the objective function on the interval of interest. If necessary, check the endpoint.
Okay, so now that we know how to do optimization, let us try and do some easy problems. So find numbers x and y satisfying the equation y plus 4x equals 20, such that the product is as small as possible. All right, so we can't use a picture, but we can identify our numbers are x and y. All right, nice. So now that we have this, let's see our objective and constraints. Our objective function is p equals x times y because we are trying to find and minimize the product as small as possible. So it's p equals x times y, p being product. Awesome. Okay, so now we have to try and find our constraints. And luckily, it's already given the entire constraints in this problem, y plus 4x is equal to 20. So that is our constraints. Awesome. So now we have to isolate a variable in the constraints. So let's isolate y because that's the easiest. So that's y is equal to 20 minus 4x. Now let's plug that in back into our objective function, and we get, okay, x times 20 minus 4x. And so that we distribute it is 20x minus 4x squared, and that is that final equation. So now when we try to find the intervals, we are trying to find any sort of restrictions or limits on this given equation, y plus 4x equals 20. But when we're seeing it, we're saying, okay, there's no limits at all, and it can be negative or positive. So that means this can be, the interval is all real numbers, or negative infinity to positive infinity in another way of saying it. So now that we have that, let's find the derivative. So p prime is equal to 20 minus 8x. Then we have to set this equal to 0 to find the critical numbers. So that would be 20 is equal to 8x, and x is equal to 5 over 2. And so we can find y by substituting that back into the constraints. So y plus 4 times 5 over 2 is equal to 20. And once we simplify, we get y is equal to 10. All right, so now that we have that, it's still asking for the product. So let's put this all back in. So p is equal to 5 over 2 times 10, and we get that p is equal to 25. So this is our final answer. The product is as small as possible when p is equal to 25.
Find two non-negative numbers whose sum is 60 and whose product is a maximum. So we cannot use a picture for this question because it's algebraic, but we can find objective function, which is p equals x times y, and 60 equals x plus y would be our constraint for this question. First, we have to isolate y equals 60 minus x so that we can plug it into the objective function, which you will get 60x minus x squared equals 0. Now we have to set it up to 0 because we have to look for the interval of interest, and you will end up getting 0 to 60 as the interval of interest. And you find derivative of p, which is 60 minus 2x, and you set that to 0, and you should get x equals 30. Now you plug 30 back into the constraint, which is 60 equals 30 plus y. Now you should get y equals 30 for the y value, and it's asking for the product is a maximum. So you multiply 30 times 30, and you will get 900 as the answer.
All right, so now that we have solved an easy problem of optimization, let us solve a medium problem of level of difficulty. So a farmer uses 1,600 feet of fencing to enclose a rectangular area which will be divided into 3 pens. What is the maximum total area of the 3 pens that he can enclose with the limited amount of fencing available? So we drew our rectangular area with the 3 pens labeled as x and y, and we have our objective unconstrained function. So our objective function is what we're trying to minimize in this case, which is the area. So area equals x times y. And our constraints is what is already given in the problem. So we know that 2x plus 4y is going to equal our 1,600 feet of fencing. So now that we have that, let us take out and isolate a variable in this constraints. So we can isolate x, and that's 800 minus 2y. Then we put this into our original equation. We get 800 minus 2y times y, and we get 800 is equal to 800y minus 2y squared. Now we have to try to find the interval. So we can set this equal to 0. And once we do that, we get 800y is equal to 2y squared. And so y is equal to 400. So this shows our interval is from 0 to 400 because first of all, it cannot go below 0. And if it goes above 400, that's also going to be a negative number. So now that we have that, let's find the derivative. So a prime is, in short, 800 minus 4y. We set that equal to 0, and we find that y is equal to 200. So if we plug that in back into our constraints, x is equal to 400. And then to find the product, we just multiply both of these, and we find that this is 80,000 feet squared. Always remember to put feet here, and always remember to use your units, and that is the answer, 80,000 feet squared.
A farmer has 600 feet of fencing and wants to create a rectangular field across a river. He needs no fence along the river itself. What are the dimensions of the field that has largest area? So I have organized the information of this problem in the picture below, and we can start from finding objective function, which is a equals x times y, and our constraint would be 600 equals x plus 2y. Alright, now we isolate x equals 600 minus 2y so that we can plug it into the objective function as 600 minus 2y into the x. Now we set 600y minus 2y squared equals to 0 to find our interval of interest. You should get 2y squared equals 600y and y equals 300, and 0 to 300 would be our interval of interest. And now we find derivative of area, which is 600 minus 4y. You set this equal to 0, and you should get y equals to 150 feet. Now we know that y equals to 150 feet. We can plug this 150 into our constraint equation, which 600 equals x plus 2 times 150, which gives you x equals 300 feet. And this is the dimensions of the field with the largest area.
Alright, so now that we have done easy and medium level of difficulty problems for optimization, let's do a hard one. So this one is not usually using the usual optimization guidelines that we have been using for the other problems, but it still is trying to optimize a certain quantity given the constraints. So let's solve it. So find the point on the line y equals 4 minus x that is closest to the point 7,6. So to save time, I've already drawn the picture. So y equals 4 minus x, I have drawn it on the number line graph, and I have put 7,6. Now, on the graph, we don't know the exact point that is closest to 7,6, so I just labeled that point x1, y1. All right? And from this, we can presume, if we draw a triangle, a right triangle, we can presume that the hypotenuse between these two values is the distance between those 2 points. So ultimately, this distance is going to help us to try and find the point that is closest to the point 7,6. All right, so now let's find our objective and constraints. So our constraints, we know is already given in the problem. It's y equals 4 minus x. Easy peasy. And then our optimization is what we're trying to minimize in this case because it says closest. And in this case, it's going to be our d, our distance. So let's write the distance formula. That's the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay? And that's this formula. So now we got to substitute in some of our variables. So we get, okay, 7 minus x squared. I also labeled 7, 6 as x2, y2. Those are the second points that we're going to compare in our distance formula. So 7 minus x squared plus 6 minus, and since we know that y is equal to 4 minus x, then we can just say that y1 is also equal to this. So we can say 4 minus x, and so this is squared, and that is what we do. So to make this easier on ourselves, we can basically make this to the power of 1/2 instead of just square rooting it. So get this, and we get to the power of 1/2. All right, so now we have to differentiate this problem. And so we can first start by using chain rule. So 1/2 of 7 minus x squared plus 2 plus x, because 6 minus 4, 2 plus x squared raised to 1/2, and then times the derivative on the inside. So that's 2 times 7 minus x times -1 plus 2 times 2 plus x times 1. Now that is our problem. So we have d prime. When we simplify this, we get 2 plus x minus 7 plus x is over square root of 7 minus x squared plus 2 plus x squared. Awesome. So now that we have this, let us set this equal to 0. So we get 2x minus 5 is equal to 0, which means that x is equal to 5 over 2. And so when we plug that in back into our y is equal to 4 minus x, which we know is 5 over 2, we get x is equal to 3/2. So those are 2 points in this problem where we know that this is the closest to 7, 6. And in this case, finding an interval is not as important because we already know that this question is already hard enough. So we can just find the points and we know, okay, this is going to be the closest. And ultimately, this is how you're supposed to find this problem's answer. X is equal to 5 over 2, y is equal to 3/2.
A rectangle is inscribed in a semicircle with a radius of 10 centimeters. What are the dimensions of the rectangle that will maximize its area? So I have organized this information as a picture below, and we can start from that. Our objective function is area equals length times width, which is the equation for the rectangle's shape, and in this case it will be 2x times y. We have to find a equation of circle because we need to isolate y squared equals r squared minus x squared. We can square root that, and we can make y equals 100 minus x squared since we are substituting 10 centimeter as a radius. Now we plug this to y into the objective function, which is 2x times y, and 2x times square root of 100 minus x squared, and we can use product rules, and we should get 2 times 100 square root of 100 minus x squared plus 2x times 1/2 times 100 minus x squared over 1/2 minus 1/2 times minus 2x, and we can simplify by multiplying 100 root of 100 minus x on both sides, and divide minus 2x squared by root of 100 minus x squared, and we should get something like this: 200 minus 4x squared, and we set this as equals to 0 so that we can solve for x, and we should get x equals root over 50. We can simplify a little bit further into it, and we should get x equals 5 root of 2. And now we can put this 5 root 2 into our constraint that we solve as a y equals 100 minus x squared, and x squared 5 root 2 squared is equal to 50, and 100 minus 50 equals root 50. So we should get 5 root 2 as the answer, and these are the answer for the maximum area of this